তোমরা শুনতে পাচ্ছ?
হ্যাঁ স্যার।
আচ্ছা, শুরু করবো তো?
হ্যাঁ স্যার।
আচ্ছা, গোড়ায় একটা কথা বলে নিই, এর আগের দিন এই যেগুলো করোলারি লিখেছিলাম না, আউট অফ মিস্টেক আমি এগুলো করোলারি লিখেছিলাম। অল দিস শুড বি লেমাস। লেমাস মিন্স স্মল থিওরেম। হ্যাঁ,
ওকে।
প্লিজ ডু দ্য necessary correction. I am sorry for this mistake. Now what do you want? Should I give some idea on how to prove these lemmas, or I should proceed further?
স্যার যেটা ইচ্ছে।
যেটা ইচ্ছে। তুমি কে? সৌর্য তো?
শুভ্র স্যার।
শুভ্র, তুমি এটা গতকালকে কি বলছিলে না, এগুলো প্রুফ করবার জন্য তুমি না কে বলছিল?
হ্যাঁ স্যার আমিই ছিলাম।
আবার হোয়াট অ্যাবাউট আদার্স? অন্যরা কি বলছে? আর দে ইন্টারেস্টেড? আমি ডিটেল প্রুফ করবো না, আমি একটা আইডিয়া দিয়ে দেবো, ব্রড আউটলাইন লজিক্যাল আইডিয়া দিয়ে দেবো কিভাবে প্রুফটা হচ্ছে। আদার্স অন্যরা কি বলছো? নীলাঘ, সৌম্যদীপ, আকাঙ্ক্ষা, রাতুল, অনির্বাণ, what is your suggestion? Respond please. I am confused. Oh, Akanksha has sent a message. It would be helpful if you could prove them, sir. Akanksha, in which discipline do you read? Are you from which discipline? PTC. Oh, achha. Okay, I am trying to give you some idea. What is lemma 1? Lemma 1 state that anytime before a star terminates, there must be a node n dot on open which is on an optimal path from S to a goal node with fn dot less than equal to f star s. How can you prove this? আসলে এইসব পড়াতে গিয়ে আমরা অনেক পিছিয়ে গেছি। যাই হোক, একটুখানি বলে দিচ্ছি। শুভ্র, তুমি প্লিজ রিড আউট লেমা 1।
Sir, lemma 1 states that anytime before A star terminates, there must be a node n on open which is on an optimal path from S
n dot
n dot which is on an optimal path from S to goal node with f n dot less than equal to f star s.
Let this be the state space. Let this be the start node. This node may have several successors. All are shown with dotted lines because initially no node was visited. So all are shown with dotted lines. Let this be the goal node. Now I am showing the optimal path, that is the least costly path from start node to goal node with red ink, with red color. Let this be the optimal path from start node to goal node. So this is an optimal path from S to goal, S to a goal. Let this be some other paths from S to a gold node. This may be another path. This may be another path from S to a gold node. And all these other paths, these paths do not lead to the goal state. The other paths do not lead to the goal state. So at the beginning, the open list, it consists of only the start node. Let this node be N0 initially. And in step 1, if this in step 2, if this node, if this list is not empty, then we remove a node, and in this case it will be N0, and we will mark it as visited, and it does not match with the goal. So what we will do, we will expand this node. We will expand this node. That means we will generate all its successors. And let us assume that this node is N1 and it may have some successor which is N2, and let this be Nk. So the sequence of nodes on an optimal path from S to a goal, it consists of what? Which nodes? Tell me. The sequence of nodes on an optimal path from S to a goal node, it consists of which nodes?
Sir, N0, N1, N2, and Nk.
Okay. N0, N1, N2, N dot, then Nk. Let this be the sequence of nodes lying over this optimal path Optimal path from where to where? From node N0 to NK. That is the goal node. Achha. Mark it as visited. Now, after node N0 is expanded, all these nodes will will be moved to the open list. Let this be N1 dot. Let this be N1 double dot. Let this be N1 triple dot. Let this be N1, then 4 dots. All these nodes will be placed on the open list. Do you agree?
Yes, sir.
Achha. So what will happen? So if this is the open list, N1 dot will be there, N1 double dot will be there, N1 will be there, N1 will be there, then N1 double dot will be there, and N1 dot N1 double dot, sorry, N1 triple dot will be there, and N1 4 dots. So all these nodes will appear on the open list after N0 is expanded.
Yes, sir.
Now out of these nodes, this red colored node, that is N1, it is on the optimal path from S to a goal node. Agreed?
Yes, sir.
Achha. Next time, out of these nodes from the open list, one will be selected.
Yes, sir.
That may be N1, that may be one from the optimal path, or that may be one from other paths. We do not know which one will be selected. Now, if N1 is selected, then next time the successor of N, if N1 fails to match with the goal node, next time the successor of N1, that is N2, will appear on the open list along with the other nodes,
Yes, sir.
along with the successors of N1. So before A star terminate, there must be one node which is on the optimal path from S to a goal node and which is on the open list,
Yes, sir.
that is before A star terminates, there must be a node N dot which is on an optimal path from S to a goal, there must be a node n dot on open, which is on an optimal path from S to a gain. Good. Do you agree with this statement?
Yes, sir.
Before S start terminate, there must be a node n dot on open along with other nodes, which is on an optimal path from S to a goal node.
Yes, sir.
Achha. Now, what will be the f value of this node? F of n dot equal to gn dot plus hn dot. Do you agree?
Yes, sir.
Achha. Now this gn dot, in this case, it will be the actual cost of the path from n0 to n dot on an optimal path from S to a goal node. So in this case, this gn dot will be equal to g star n dot plus hn dot, since n dot is on an optimal path. Do you agree?
Yes, sir.
Now, A star is an admissible graph search algorithm. That is, for A star, the condition is that heuristic function will be so designed that it will never make an overestimation of the actual cost of the optimal path joining start node to a goal node. Mathematically speaking, for A star, Hn is less than equal to H star n for all nodes n. Do you agree?
Yes, sir.
So what is F star n dot n? No. Okay. Now this so h of n dot is less than h star n dot, and let us add g star n dot in both sides. G star n dot plus h of n dot is less than equal to h star n dot plus h star n dot. Do you agree with this inequality?
Yes, sir.
Do you agree with this inequality? This g star n dot plus h n dot is equal to actually f of n dot, as we have shown here,
Yes, sir.
less than equal to f star n dot.
Yes, sir.
Now what is n dot? N dot is a node on an optimal path from start node to a goal node. So this f star n dot is basically it is equal to f star s. So this is less than equal to f star s. দেখো প্রমাণটা হলো।
হ্যাঁ স্যার।
So lemma 1 has been proved. ঠিক আছে?
হ্যাঁ স্যার।
আচ্ছা, next please read out the statement on lemma 2.
স্যার একটু দাঁড়ান, লিখে নিও এটা। ডান দিকেরটা তো ছেড়ে দিন, বাঁ দিকেরটা হয়ে গেছে।
লেখা হয়েছে?
স্যার হয়ে এসছে। স্যার একটু সরে যান স্যার। হ্যাঁ স্যার হয়ে গেছে।
আচ্ছা, মুছে দিচ্ছি। এবার লেমা 2 স্টেটমেন্টটা বলো।
Sir, algorithm A star must terminate for state space graph having finite branching factor and positive arc cost for all arcs.
ফাইনাইট ব্রাঞ্চিং ফ্যাক্টর মানে কি? যে if this be a node in the state space, the number of successors of this node, let n a node on the state space graph. So finite successors means that the number of successors of A, it must be equal to a finite number. Agreed?
Yes, sir.
It may be 100,000, million, trillion, anything, but it must be a finite number. It must be a finite number. It cannot be as high as you think.
Yes, sir. বুঝেছি স্যার।
আচ্ছা। Secondly, let epsilon be the arc cost between these two nodes. This epsilon must be greater than 0. That we are assuming. It cannot be negative. It cannot be 0.
Yes, sir.
Achha. Now, under such situation, is there a possibility of a state space graph being infinite?
No, sir.
Why? It may have, there is no, the number of nodes in this graph, it is not finite. It may not be finite, sorry. Only the branching factor of a node is finite. But the number of nodes number of nodes in this graph, that may not be finite. That may be as large as you think of it.
Okay, sir.
So this there is a possibility that this state space graph may be an infinite graph, since the number of nodes in this graph need not necessarily be a finite number, but the branching factor must be finite.
Yes, sir.
So there is a limit on the breadth-wise growth of this state space graph. Breadth-wise, this graph cannot be as long as you think of it, but height-wise, it may be as long as you think of it.
Okay, sir. Understood.
So we cannot rule out the possibility of an infinite state space graph, which we assumed initially.
Yes, sir.
Follow my
Yes, sir.
argument?
Yes, sir.
Okay. Then please read out lemma 2 again.
Sir, algorithm A star must terminate for all state space graph having finite branching factor and positive arc cost for all arcs.
Now, there are two kind of termination for the graph search algorithm. Under if it finds the open list to be empty while removing a node from the open list, if it finds that the list is empty, it will terminate.
Yes, sir.
And that
Exactly.
termination occurs if the entire graph is searched and it fails to find a goal node. That is a situation where there is no path from start node to a goal node in the state space graph.
Yes, sir.
Under that situation, if the graph is finite, then that kind of termination may occur.
Yes, sir.
Now, when I mentioned the statement of the main theorem, that is algorithm A star is admissible. There I mentioned algorithm A star is admissible. That means it is guaranteed to provide you an optimal path joining start node to a goal node. If at least one such path exists, that means when we are proving this theorem, we are assuming that at least one path joining start node to a goal node exists.
Yes, sir.
So that kind of termination, that will not happen here.
Yes, sir.
Okay.
Yes, sir.
That kind of termination occurs under two conjunctive situation. Number one situation is there is no path joining start node to a goal node. Number two situation is the state space graph is finite. Under these two conjunctive situation, that kind of termination occur. So on the basis of the assumption that we are on which we are going to prove this theorem, there is no possibility that kind of termination will arise. We need not consider that kind of termination.
Yes, sir.
So what kind of termination may occur or may not occur? That is whether it will terminate after finding a goal node. That is the question now, isn't it?
Yes, sir.
Okay.
Yes, sir.
And we will prove this lemma through contradiction. That means initially, let us assume let A star does not terminate on finding a goal node. So this is our assumption. That is, we are thinking in contrary to the statement of the lemma.
Yes, sir.
Next, we will analyze what will be the consequence of such assumption. The consequence is this: for an infinite graph, A star algorithm will continue and continue.
Yes, sir.
More and more nodes will be added to the open list.
Yes, sir.
And the depth of the search tree will go on increasing and increasing.
Yes, sir.
And as the depth of the search tree goes on increasing and increasing, for the value of Fn, this Gn will also will increase and increase.
Yes, sir.
Right?
Yes, sir.
As the Gn goes on increasing and increasing, the Fn value for the nodes which are on the open list will go on increasing and increasing.
Yes, sir.
So we cannot impose a limit on the F values of the nodes on the open list under this situation. It may be as large as we think, because we have assumed that this algorithm will not terminate.
Yes, sir.
So under that situation, before a start termination, there will be no node n dot on open list which is on an optimal path and whose F value is less than equal to F star S. This condition will not hold, will be violated.
Yes, sir. Yes, sir.
But in lemma 1 we have already proved that if there exists at least one path from start node to a goal node, this must happen.
Yes, sir.
So this assumption leads to a contradiction that violates the lemma 1 that we have proved.
Yes, sir.
Hence it is false.
Yes, sir.
And we are working under two-valued logic. So if it is false, then what will be true? That A star must eventually terminate if there is a path joining start node to a goal node.
Yes, sir.
Hence, we prove lemma 2.
Yes, sir.
So what is the statement of the lemma 3?
স্যার লেমা 3টাও তো এটা দিয়ে প্রুফ হয়ে গেল। লেমা 3 বলছে এ স্টার মাস্ট টার্মিনেট বাই ফাইন্ডিং আ গোল নোড। আমরা এর উল্টোটাই এখনই ইয়ে করলাম তো এক্ষুনি।
হ্যাঁ, এটা দিয়ে প্রুফ হয়ে গেল।
হ্যাঁ,
এবার লেমা 4টা বলো।
A star must terminate by finding a goal on an optimal path from S.
আচ্ছা। Now a problem may have several goals. A problem may have several goals. Let this be G1, let this be G2, let this be G3, let this be start node. Let this be the optimal path. And out of all these paths, one will be optimal.
Yes, sir.
Now we have proved that A star must terminate by finding a goal node. That we have proved. But that may be G3, that may be G1, that may be G2. Unless it is G1, that it is guaranteed to be G1, we cannot prove that A star must terminate by finding a goal node on an optimal path joining to start node.
Yes, sir.
So again we will prove it through contradiction. Let A star terminates on finding a goal G dot on a non-optimal path to S. Can you follow the assumption that we have made here initially?
Yes, sir.
In that case, G dot must be on the open list because it is selected. And before A star terminates, there must be an N dot according to the lemma 1, which is on the optimal path joining start node to a goal node. That means N dot will be somewhere here. So this f of G dot, it is greater than f star s. Do you agree?
Yes, sir.
Since it is not on an optimal path from start node to a goal node. And again, by lemma 1, f of n dot is less than equal to f star s. What is f of n dot? F of n dot is basically f of n dot is basically
G of n dot plus H of n dot.
f of n dot basically f of G, where is on an optimal path, because n dot is on an optimal path. Agreed?
Yes, sir.
So from here, what we can write? F of G, it is less than equal to f star s.
Yes, sir.
Can this happen? Because f star is the actual cost of the optimal path joining start node to a goal node.
Yes, sir.
Now, can f of G be less than f star s? Because G is a node on an optimal path.
Yes, sir.
So it must be exactly equal to f star s. It
Yes,
can
sir.
never be less than equal to f star s.
Yes, sir.
So hence it leads to a contradiction in the existing lemma that we have proved earlier.
Yes, sir.
So what is the opposite truth? That A star terminates by finding a goal node on an optimal path to a start node.
Yes, sir.
Hence we prove the theorem. ঠিক আছে?
হ্যাঁ স্যার। স্যার 1 মিনিট দাঁড়িয়ে। স্যার হয়ে গেছে।
মুছে দেবো?
হ্যাঁ স্যার।
স্যার নিলসনের বইয়ে প্রুফ আছে, প্রুফ দেখে নেবে। আমি মানে লজিকটা বলে দিলাম, মেজর স্টেপস গুলো বলে দিলাম, আশা করি কনসেপ্টটা বোঝা গেল।
হ্যাঁ স্যার, বুঝে গেছি।
জানি না সবাই বুঝলো কিনা। আচ্ছা, আমি একটা করোলারি দিচ্ছি, এটা তোমরা এটা নিজেরা প্রুফ করবে, চেষ্টা করবে, তাহলে এটা বইয়ে আছে, বই থেকে দেখে নেবে। এটা আর আমি প্রুফ করছি না, ভেরি ইজি। A corollary to this theorem. It is a corollary, mind it. It is not a lemma. Now I am stating a corollary. Corollary to what? Which theorem? That A star is admissible if there is at least one path joining start node to a goal node. So when the A star algorithm runs, it will select nodes from the open list several times. And for all such nodes, this inequality will hold. That is, for any node A selected for expansion by A star, the F value of that node must be less than equal to F star S. That is the actual cost of the optimal path joining start node to a goal node.
Yes, sir.
This you can prove assuming lemma 1. আচ্ছা, আমি 1 মিনিট আসছি বাইরে। এটা মুছে দিচ্ছি।
হ্যাঁ স্যার।
দেখি কজন আছে। Next topic I am going to discuss is how to increase the heuristic power of an evaluation function. This is the evaluation function. Fn equal to Gn plus Hn. Now first let us discuss what we mean by heuristic power. Here we have used a heuristic function. This is called heuristic function. Why we have used here? What is the purpose of using heuristic function here? Can anyone explain? দেখি চ্যাট বোর্ডে বলো।
Sir, to provide domain specific knowledge.
Why do we need this domain specific knowledge? For what purpose? We are going to utilize domain specific knowledge.
Sir, to estimate the actual cost of the least cost path from a node n to the goal.
That means by using this knowledge, by using this heuristic function, we want to estimate how far the goal node is from node n in the state space graph.
Yes, sir.
Isn't it?
Yes, sir.
By using this heuristic function, we want to estimate, we want to make an estimation of what? Of how far a goal node is from node n in the state space graph. The more will be the distance, the higher will be the value of this heuristic function.
Yes, sir.
Now, so this is the purpose of using heuristic function. Now, what is the significance of a powerful heuristic function? When we will call this function a powerful one?
When it gives close to accurate results.
Achha. And with that result, what benefit we will get? If we can estimate the position of a goal node from node n in the state space graph more accurately, then what advantage we can have during this search process?
Sir, we can get the path to the goal node faster.
faster. That means by probing lesser number of nodes, by expanding lesser number of nodes, we will be able to find the goal node. If the heuristic function is sufficiently powerful.
Yes, sir.
And by expanding lesser number of node means with lesser computation. With lesser computation, we will be able to reach the goal node if this heuristic function is sufficiently powerful.
Yes, sir.
And if this heuristic function is sufficiently powerful, obviously this evaluation function Fn will also be powerful in respect to its heuristic power.
Yes, sir.
Now there is again some experimental evidence. It is not a theorem, it is not a proven fact that if you allow this Hn to be prominent in this sum, to play a prominent role in this sum, to contribute significantly in this sum, if you allow Hn to contribute significantly in this sum, I repeat, if you allow Hn to contribute significantly in this sum, there is a possibility that you will get a powerful heuristic function. That means with a powerful heuristic function, you will be able to reach the goal node much earlier by expanding lesser number of nodes. You will be able to reduce computation in relation to node expansion.
Yes, sir.
It is not a proven fact, but certain experimental evidence suggests that if we allow Hn to contribute significantly in this sum, there is a good possibility, there is a good chance that the goal node we will be able to reach the goal node earlier.
Yes, sir.
Now, what is the problem of allowing Hn to make significant contribution in this sum?
স্যার একবার রিপিট করুন একবার রিপিট করুন
What is the problem that we may face by allowing Hn to contribute significantly to this sum? Before that, let us discuss how we can allow Hn to contribute significantly to this sum. How we can allow Hn to contribute significantly.
Sir, Hn should be much greater than Gn.
Significantly to the sum. Or in other words, how we can make Hn to play more prominent or significant role compared to GN. Compared to GN. How we can make HN to play more prominent or significant role compared to GN? That is, we can do this by relaxing the admissibility criterion. Admissibility criterion on HN. আমি একটু মুছবো, নিচের দিকটা মুছবো।
হ্যাঁ স্যার।
By relaxing the admissibility criterion on HN, that means by relaxing the condition that Hn is less than equal to H star n for all n. If you relax this condition, then we will be able to allow H to contribute more significantly.
রিল্যাক্সিং করা মানে বুঝলাম না ব্যাপারটা।
রিল্যাক্সিং করা মানে আমরা আর অ্যাডমিসিবিলিটি ক্রাইটেরিয়াটা ইম্পোজ করব না। এ স্টার অ্যালগরিদমটা কি?
হ্যাঁ স্যার।
uses an additive heuristic function
Yes,
fn
sir.
equal
Yes,
to Hn plus Hn, but there is a constraint, there is a restriction. What is that? That you should design heuristic function in such a way that it will never be allowed to make an overestimation of the actual cost of the optimal path joining node n to a goal node.
Yes sir.
And we are relaxing this criterion. That means we are relaxing the admissibility criterion on the heuristic function. এক minute. সো
স্যার একটা কোশ্চেন ছিল।
হ্যাঁ বলো বলো।
হ্যাঁ, বলছিলাম যে যদি আমরা অ্যাডমিসিবিলিটি ক্রাইটেরিয়াটা রিলিজ করে দিই
রিল্যাক্স করি, রিলিজ না রিল্যাক্স করি।
হ্যাঁ রিল্যাক্স করে দিই, তাহলে তো এটা বেসিক্যালি ওই এ অ্যালগরিদমটাই চলে এলো আবার।
হ্যাঁ,
তাহলে তো এটা সেই এ অ্যালগরিদমটাই চলে এলো।
কোন অ্যালগরিদম? অ্যালগরিদম
এটা
এটা আছে।
এ অ্যালগরিদম।
হ্যাঁ, ওই ব্যাপারে আসছি, ওই ব্যাপারে আসছি, ওই ব্যাপারে আসছি। আসছি, ওই ব্যাপারটা বলছি। দেখো কি পড়লাম, একটু রিড আউট করো তো দেখি কেমনি পড়তে পারছো।
Experimental evidence suggests that in some cases, by relaxing admissible criterion, the total number of node expansion for finding a goal may be reduced. But this will disturb the guarantee of having an optimal solution provided by A star.
মানে বুঝতে পারলে?
হ্যাঁ স্যার, মানে যে থিওরেমটা আমরা বা লেমা দিয়ে প্রুফ করলাম ওইগুলো তো আর প্রুফ হবে না যদি আমরা ওই অ্যাডমিসিবিলিটি ক্রাইটেরিয়াটা না ধরি।
That means, আচ্ছা, why it happens? It may not provide the optimal solution. You can also have an optimal solution. Sorry. The chance is not nil. The chance of having an optimal solution by using an inadmissible heuristic function, by relaxing the admissibility criterion on the heuristic function, the chance for having an optimal solution is not nil. Mind it, the guarantee cannot be provided, but you may also have the optimal solution. That is a matter of chance. There will be no guarantee. Only
Yes,
point
sir.
is this.
বুঝতে পেরেছি।
বুঝতে পারলে?
হ্যাঁ স্যার।
আচ্ছা। Now the question is this: you have to set the priority. If reducing computation becomes the only priority, then you can try in this fashion. But if having an optimal solution is the only priority, then you will not be allowed to relax the admissibility criterion. Since most of the AI problems are real world problems, are very much computationally intensive, very much computationally intensive. Since most of the AI problems require huge computations, because of this exponential order of time and space complexity of this general graph search algorithm, for real world problems, for real world AI problems, huge computations are required. So most of the time it will be our priority to reduce the computation using proper heuristics, using good heuristics, and and we may take a chance by relaxing the admissibility criteria.
Yes, sir.
It is a matter of chance whether we will be able to reduce the number of node expansion. That is also a matter of chance. But experimental evidence suggests that in some cases, by relaxing admissibility criterion, the total number of node expansion for finding a goal may be reduced.
স্যার বুঝতে পেরেছি।
Achha. Next point is we can artificially or we can mechanically enhance the contribution of heuristic function in this sum. How? By using weighted heuristic function, we can mechanically, we can forcefully enhance the contribution of HN in this sum. Thereby, we may take a chance to reduce the computation relating to node expansion during the search process.
Yes, sir.
But in these cases also we have to relax the admissibility criteria. Now, previously what we discussed, by using an inadmissible heuristic function, we may try. By using an inadmissible heuristic function, we may try. Try for what? We may try for reducing computation relating to node expansion. Achha. There is another advantage we may have by using an inadmissible heuristic function. It is that usually the computation for an inadmissible heuristic function is much simpler compared to an admissible heuristic function. However, here we are forcefully enhancing the contribution of Hn in this sum. We are forcefully prioritizing heuristic component in this evaluation function. By using this, we can also try to enhance the heuristic power of an evaluation function.
Yes, sir.
There are also methods where this W is varied, where now, okay, I shall explain this later. But before that, we can artificially enhance the contribution of Hn in this evaluation function by weighting its values with some value greater than 1. It is true. But this may hamper the chance of getting an optimal cost solution fast. Isn't it?
Yes, sir.
Now, instead of having an optimal cost solution path, we may try to have a near optimal solution path. How we can do this? If nothing is guaranteed here, all are uncertain, because the knowledge we are using, it is not 100% true. It may not be 100% true in the real world situation. But these are various possibilities which may be tried. What is that? When the node n is at lesser depth, that is when it is far from the goal node, it is far away from the goal node, rather it is closer to the start node, what will be our priority? Our priority will be to reach the goal node as early as possible by reducing the computational cost relating to node expansion.
Yes, sir.
When node n is far away from the goal node in the state space. When it is near the start node, the priority is to reduce the computation.
And increasing accuracy.
Accuracy means whose accuracy?
মানে গোলটা পৌঁছানোর অ্যাকিউরেসিটা মানে
না,
আপনি বললেন না সব
অ্যাকুরেসি কিছু, অ্যাকুরেসি তো এই চেঞ্জ যা দেবে তাই, এই
হ্যাঁ,
চেঞ্জে তো আমি হাত দিইনি।
না না বলছিলেন না যে গোলে পৌঁছাতে মানে রিয়েল ওয়ার্ল্ডে না পৌঁছাতে পারে গোলে,
হ্যাঁ,
আপনি বললেন না গোলে না পৌঁছাতে পারে রিয়েল ওয়ার্ল্ডে।
না না, গোলে না পৌঁছতে পারে বলিনি, গোলে তো পৌঁছবেই।
আচ্ছা,
ব্যাপারটা হচ্ছে যদি অ্যাডমিসিবল হিউরিস্টিক ইউজ করে তাহলে তো গ্যারান্টেড ওর সলিউশন দেবেই, গোলে পৌঁছবেই।
হ্যাঁ
ঠিক আছে,
হ্যাঁ হ্যাঁ
আচ্ছা, প্রশ্নটা হচ্ছে উই মে নট গেট দ্য অপটিমাল সলিউশন।
ইয়েস স্যার।
আচ্ছা, এবার কি বলছি যে এই যে আমরা এই চেনটা ইউজ করছি, এই যে নলেজটা আমরা ইউজ করছি, এই নলেজটা তো 100% কারেক্ট নলেজ নাও হতে পারে। ফলে আমি যে ক্লেম করছি যে এই চেন ইউজ করে আমি কম্পিউটেশন রিলেটিং টু নোড এক্সপানশন আসলে কমাবো, তাড়াতাড়ি গোল নোডের কাছে পৌঁছে যাব, এটা আমি যেভাবে ভাবছি সেভাবে নাও হতে পারে। হিউরিস্টিক্স মে ফেল।
ইয়েস স্যার।
দ্যাট ইজ আই এম টেলিং।
ইয়েস স্যার, আন্ডারস্টুড।
বলে পৌঁছাতে পারে, পারে কি পারে না বলছি না।
হ্যাঁ 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 ঠিক আছে, হ্যাঁ হ্যাঁ বুঝতে পেরেছি।
এবার যেটা বলছি, এবার যেটা বলছি যে when we are far away from the goal node for a very large state space, as it happens in the real world situation, when we are far away from the goal node, when node n is at lesser depth, when node n is closer to the start node, what will be our priority? Our priority will be to reach the goal node as early as possible.
Yes sir.
And for that, when node n is at lesser depth in the state space, we may make the value of w high to enhance the contribution of heuristic in this evaluation function. We can magnify it artificially by multiplying it with a large value of w. Right?
Yes sir.
But as the search proceeds towards the goal, as the depth of the node increases, our priority will change. When node n is closer to the goal node, our priority will be to visit as many paths as possible which lead to the goal node, because at that time our priority will be to reach the goal node with a less costly path. And how we can implement this? By reducing this weight value when n will be closer to the goal node. That is also another technique. That is, the value of w may also be varied inversely with the depth of node n.
Yes sir.
Thereby, we may make an attempt to have a near optimal solution path.
Yes sir.
So all this I am discussing to explain how the heuristic power of an evaluation function can be increased. Okay?
Yes sir, understood.
Next point is, what is the role of this GN? What is the role of this GN? Next point is, it is not related to heuristic power. It is a separate issue. You should not confuse the role of GN with heuristic power. What is the role of Gn in this evaluation function? Before discussing this, let us recollect what we discussed under breadth first search. Breadth first search. Can you recollect it?
Yes, sir.
I mentioned that under breadth first search, if you assume the arc cost to be unity, you will always get the least costly path joining start node to a goal node. Can you
Yes, sir.
recollect it?
Yes, sir.
Because breadth first search proceeds level after level. That is, it first searches nodes of all the depth of level L, then it searches the nodes of all nodes of level L plus 1.
Yes, sir.
It is unlike the case of depth first search. Depth first search does not guarantee the least costly path from start node to a goal node, assuming the arc cost to be unity. But the breadth first search guarantees, it can provide a guarantee for providing the least costly path joining start node to a goal node, assuming arc cost to be unity. Right?
Yes, sir.
So why it is so for breadth first search? Because breadth first search ensures that all portion of the graph must be searched.
Yes, sir.
Now here in this evaluation function, the necessity of Gn is that it adds a predominantly breadth first component to this search process. That means this is to ensure that graph search algorithm must not terminate without finding a goal if at least এটা কি হবে, if at least one path from S to a goal exists.
হ্যাঁ স্যার, বুঝতে পেরেছি।
ফলে জিএনটাকে আমরা বাদ দিতে পারছি না।
হ্যাঁ স্যার।
আচ্ছা, আমি একটা কথা বলছি, আমি যদি এই চেনটাকে বাদ দিয়ে দিই তাহলে কি হবে? দেখো, এটা মুছে দেবো।
হ্যাঁ স্যার। স্যার এই চেনটাকে বাদ দিলে তো সেই ব্লাইন্ড সার্চ হয়ে গেল।
না, ব্লাইন্ড সার্চ হলো, ব্লাইন্ড সার্চ মানে কি? ব্লাইন্ড সার্চ মানে ডেপথ ফার্স্ট বা ব্রেথ ফার্স্ট হচ্ছে না কিন্তু এখন।
হ্যাঁ।
এখন কি হবে? এখন যার জি ভ্যালুটা যে নোডের ছোট হবে সেই নোডটাকে সিলেক্ট করবে।
হ্যাঁ হ্যাঁ হ্যাঁ।
আচ্ছা, দ্বিতীয় কথা হচ্ছে এখন কিন্তু আমি ওই ব্রেকফাস্ট সার্চে নেই, এখন আর্ট কস্টটা যে ইউনিটি তার আমি বলছি না, আর্ট কস্টটা শুধুমাত্র পজিটিভ, এইটুকুই বলছি। কথাটা বুঝলে কি
হ্যাঁ স্যার,
বললাম?
বুঝেছি।
ঠিক আছে,
হ্যাঁ স্যার।
ইকুয়াল টু জিএ, আর্ট কস্ট আর অল পজিটিভ।
হ্যাঁ স্যার।
তাহলে এবার কিরম ভাবে হবে সার্চটা? যে সব সময় যে নোডগুলোর কস্ট অফ দ্য পাথ জয়েনিং
স্টার্ট নোড কম থাকবে সেটা আগে হবে। হ্যাঁ।
যেগুলোর মিনিমাম সেগুলো আগে হবে,
হ্যাঁ স্যার। হ্যাঁ স্যার।
তাই তো?
হ্যাঁ স্যার, বুঝতে পেরেছি।
তা মানে কি, সমস্ত একই কস্টের নোড এন গুলো আগে ভিজিটেড হয়ে যাবে, তারপরে কস্টের গুলো তারপরে হবে।
হ্যাঁ স্যার।
সেই জন্য এইরকম যখন হয় এটাকে বলে ইউনিফর্ম কস্ট সার্চ, বুঝলে?
হ্যাঁ স্যার।
Uniform cost search. It is guaranteed to provide you the least costly path if at least one path from start node to a goal node exists. ঠিক আছে?
Yes sir.
But only point is this: since you have made the heuristic component 0, you may not conduct the search efficiently.
Yes sir.
That is the difficulty of using uniform cost search.
Yes sir, understood.
আচ্ছা, এবার আমরা যদি শুধু এই চেন রাখতাম তাহলে কি হতো দেখো, এটা বুঝবো?
স্যার একটু দাঁড়িয়ে যান,
আমার কথাগুলো লিখে নিও, what I have mentioned.
হ্যাঁ স্যার, ঠিক আছে।
Uniform cost search,
হ্যাঁ হ্যাঁ।
it provides a guarantee, it guarantees to provide the least costly path from start node to a goal node if at least one such path exists. But under uniform search, the efficiency of search algorithm is completely ignored. The question of efficiency is completely ignored under uniform search. Uniform cost search, একে বলে UCS. ঠিক আছে?
হ্যাঁ স্যার।
এবার বুঝবো?
হ্যাঁ স্যার।
আচ্ছা, এবার দেখো আর একটা কথা বলি। Now, if we use Fn equal to Hn, then what will happen? Here we ignore the breadth first component of the evaluation function. So what will happen? It may so happen that we may get the solution path from start node to a goal node much earlier with lesser computation relating to node expansion. It may happen.
Sir, it might not give the shortest path.
Optimal path. Moreover, since we are completely dropping the breadth first component here, this kind of search, it is called greedy search. Greedy search, or in some book, best first search. May terminate even before may terminate before finding a goal, even if there is a path from S to a goal. So greedy search may terminate before finding a goal, even if there is a path from S to a goal. There is no guarantee that if there is a path joining start node to a goal node, that greedy search will eventually be able to find that path. Since
Yes, sir.
we are not adding the predominantly breadth first component here, the search may terminate earlier without finding the goal node. কেউ একটা প্রশ্ন করছে দেখি, can you please explain why it won't? কে প্রশ্ন করেছে? দেবব্রত গড়াই, can you please explain why it won't reach a goal? Devobroto, your answer lies to what I described last, that the evaluation function Nielsen has developed, it is an additive evaluation function. There are two functions, Gn and Hn. Gn has a special role. What is that role? Firstly, it attempts to concentrate the search in the neighborhood of the least costly path. Gn has this role, firstly. Secondly, Gn adds a predominantly breadth first component to the search process. Gn ensures that the entire graph be searched for finding a goal node. Gn ensures that search process will not terminate before the goal node is found. Before the goal node is found. That is ensured by Gn. So if you drop this component Gn from the function, it may happen even if there is a path from start node to a goal node, search process may miss it, search process may terminate without finding that path. Devobroto, কি বুঝলে? Understood, sir. Thank you. ঠিক আছে, thanks for your question. এতক্ষণ বাদে একটা কোশ্চেন পেলাম, আমার খুব আনন্দ হচ্ছে। আচ্ছা, আজকে এই অবধি থাক, ঠিক
ঠিক আছে
আছে?
স্যার। হ্যাঁ স্যার।
নেক্সট ডে উই উইল ডিসকাস জেনেটিক অ্যালগোরিদম। আজকে আর পারছি না, আজকে আর ভালো লাগছে না। ঠিক আছে?
হ্যাঁ স্যার।
আচ্ছা, এ আমি দেখছি এই একটা দুটো পেপারের ফার্স্ট পেজ তোমাদের ছবি তুলে পাঠিয়ে দিচ্ছি, তোমরা নেটে সার্চ করে ডাউনলোড করে নিতে পারবে।
স্যার কিসের?
পেপার অন জেনেটিক অ্যালগোরিদম পড়তে হবে তো।
হ্যাঁ হ্যাঁ।
বই পড়ছো, এসব যেসব পড়াচ্ছে এগুলো বইয়ে পড়ছো?
হ্যাঁ স্যার, নিলসন।
প্রোগ্রাম লিখতে বলেছিলাম।
হ্যাঁ স্যার, ওই 8% লিখেছিলাম।
তুমি কি সুব্রত?
হ্যাঁ হ্যাঁ।
তোমাকে বললাম না একটু আমার কাছে এসো,
হ্যাঁ স্যার, যাবো।
যেদিন ক্লাস থাকবে না একটু এসো, তোমার সাথে ডিসকাশনের আছে।
ঠিক আছে স্যার, ঠিক আছে।
যেহেতু তুমি লিখছো, অন্য যারা লিখছে প্রোগ্রাম তারাও আসতে পারো, নো প্রবলেম। আমি সবাইকেই ইনভাইট করছি। কেন এইভাবে হয় নাকি? এরকম কারোর সাথে কোনো মানে ফিজিক্যাল ইন্টারাকশন নেই, কথাবার্তা নেই, সামনাসামনি ইন্টারাকশন নেই। যাই হোক, তাহলে on Monday, next Monday at 4:30 p.m. we have a scheduled class and
Yes, sir.
we will discuss genetic algorithm. আমি দেখছি তোমাদের কিছু ওই পেপারের ফার্স্ট পেজটা ছবি তুলে পাঠিয়ে দেওয়ার চেষ্টা করছি, তাহলে তোমরা নেটে ওটা ডাউনলোড করে নিয়ে একটু পড়ে নেবে।
ঠিক আছে স্যার।
ঠিক আছে, ঠিক আছে, থ্যাংক ইউ। আজকে এই অবধি থাক, আমি পাঠাচ্ছি এক্ষুনি।